Hello, my name is Berend Smit, and we continue in this video our lectures on advanced molecular dynamics simulation. And advanced molecular dynamics simulation we call simulations at constant temperature. And let's start with doing something completely wrong. It's always useful to start showing you how not to do things. So, what is it? Okay, so a very naive approach, or if you think about it, why don't we simulate at constant temperature by simply keeping the kinetic energy constant? After all, if we have if we know this is the way we calculate the temperature, we just look at the total kinetic energy and we use equipartition to calculate the temperature of our system. And what we can very simple do is, if we would like to know to fix the temperature, we can compute the instantaneous temperature using this formula, and by rescaling all velocities we can simply keep any simulations at exactly the temperature we would like to have. And in fact, this is typically what we would do during the initialization step. You rescale the velocities to make it sufficiently close to the temperature you're interested in. So why is it we cannot simply use this formula to ensure that the temperature and that the kinetic energy corresponds to exactly the temperature we're interested in? So why is it we cannot use that? So, and for that, we need to look a little bit more carefully at the statistical thermodynamics, and we need to define a little bit better what do we mean by constant temperature. Well, actually, what we want to do is we want to simulate the NVT ensemble, not an ensemble that has a constant kinetic energy. We want to have a simulation in the NVT ensemble. So basically what that means, that NVT ensemble, is that we have a system at interest that is coupled with a bath, and this bath is basically ensuring that the temperature is constant. But if our system is sufficiently small, it doesn't mean that every single time this kinetic energy is exactly the same corresponding to this temperature. In fact, what we will see is if we have a finite system, the temperature, the instantaneous temperature, does fluctuate. And it's therefore important to ensure that those fluctuations are correctly captured with our simulations. So let's see if we can quantify that. Okay, so what is it we need to simulate? So here we go back to our partition function. But here is the partition function that in which we include the momentum part, because this time it's important to also consider the momentum part. So what do we have here? A partition function is to integrate over all possible configurations, where now the configurations include the momentum part, the positions part, where each configuration is weighted by its Boltzmann weight. So this is the Boltzmann weight, where here we have the Hamiltonian, and the Hamiltonian is the sum of the kinetic energy and the potential energy. So this term was there to ensure that for a system in which the particles are indistinguishable, and this Planck constant was to make sure that we can normalize the system in an identical way that a classical particle becomes equivalent to a quantum particle in a box. Where are those terms coming from? So here we have this Hamiltonian, which is the sum of the kinetic energy, which we see here, and a potential energy, which we assume doesn't depend on the momenta, which is the case for most potential energies. So let's now look at the probability to find a particular value of the momenta. So we are interested here to find what is the probability to find a particular value of the momenta. So the way you do that is you use this delta function. So it's like an ensemble average. So we calculate over, we integrate over all possible configurations, and we just want to know the probability of finding this particular configuration over its normalization constant. So this is the way we would calculate the ensemble average. So let's calculate this. And this is basically, if you substitute that, you get this, the famous Maxwell distribution. So this is something you may have seen in physical chemistry courses. This probability is just the Maxwell distribution. Okay, and this is then the with the normalization constants, which you can get from integrating the partition function. And since these are Gaussian integrals, of this form, we can do this analytically. Okay, so what does that mean? So is constant temperature, meaning the temperature is constant, meaning that the temperature does not fluctuate. So if we look at the temperature, then we need to calculate the ensemble average of the temperature, which is the ensemble average of the kinetic energy. And if you do this, you get the ensemble average. So if you, this is the sum over all particles, you can put the ensemble average here, and that is by definition an average over the momentum squared of all the particles. And this is then something you see is, as you would expect, independent of the number of particles. So you see the average temperature is related to the average kinetic energy. This is nothing special. Now what is important, and that is what we mentioned, now let's look at the fluctuations of the momenta. Because if we would impose that at every single time step, the kinetic energy is identical to the instantaneous, or to the desired temperature, the fluctuations would be zero. But is that correct? So here we have the fluctuation formula, which we look at the, if we have a Gaussian distribution, the standard deviation squared divided by this, this value squared. And if you substitute it, you get these terms here. Well, since they're all Gaussian integrals, we can compute them. So we need to compute this one and this one with this probability distribution. And since this is a Gaussian integral, we can do these integrations, these calculations of these two ensemble averages analytically. So here you see the integral p squared. You keep, since this is in 3 dimensions, you get 4 pi p squared dp if you make them in spherical coordinates, and if you do this, you get 3m over beta. Okay, as you would expect. For this one, if you do this one, we do this integration, and you get this value here. You can do this, you can check whether this is done correctly. So if we substitute that, you get 2 over 3. So for the fluctuations of the momenta, but we wanted to know what is the consequences of this for the temperature. Well, for the temperature, the fluctuation formula is like this. It's very similar, but just for the temperature. So if we substitute now these expressions, we get this term, and we get this term, and now we see an important difference. We see the n term is here. And what you see, those fluctuations, they depend on the number of particles. So unless the number of particles is infinite, there are fluctuations in the temperature. So if we would make instantaneous correction by this velocity scaling, we wouldn't capture the fluctuations correctly. So somewhat surprisingly, constant temperature doesn't mean that the instantaneous kinetic energy is always the same. No, there are fluctuations, and the fluctuations can be actually surprisingly large. It depends on the system size. So that is sort of the important message. So constant instantaneous kinetic energy is not the same as constant temperature, because in the canonical ensemble, because the canonical ensemble has fluctuations, and those fluctuations depend on the number of particles, and we need to take that into account correctly. So how we can do that will be the topic of the next presentation.